Okay, let's talk about inverse trig functions. First of all, look at what's on the screen now. This is the graph of the sine function. Remember when we talked about inverse functions in general in an algebraic sense, the idea was that for an inverse function to exist, the graph had to pass the horizontal line test. And certainly the sine function does not. If you have a horizontal line that is between -1 and 1, the line crosses the graph of the sine function lots of places, too many places, so that it's not a one-to-one function and an inverse function doesn't exist. The way around that is to realize that what's going on is for a particular horizontal line, every place it crosses the graph of the sine function represents an angle whose sine is that value. And there are lots of them if you pick a value between -1 and 1. But if you restrict the domain of the sine function, then you can make it so that there is only one angle that works. In particular, if we go from -π/2 to π/2, that has the effect of restricting the domain so that only one angle in that interval, an angle from -π/2 to 0 or 0 to π/2, an angle in quadrant 4 or in quadrant 1, will have the property that one of those angles will have a value that is a unique value for the sine function. So we're going to restrict the domain to be the interval from -π/2 to π/2, and on that interval, every value that the sine function takes on, it happens, and it happens at exactly once. So that is a reasonable choice to make for a restricted domain, to have a function that's one-to-one, to have a function that has an inverse. So the inverse sine of x is going to be restricted to values for angles between -π/2 and π/2. Then for a choice of angles in that interval, every sine value function happens exactly once between -1 and 1, and will have a well-defined inverse function. So this equation interchanges the roles of the x variable and the y variable. Y equals sine inverse of x is equivalent to x is sine of y. So that this inverse here doesn't mean the reciprocal, which you might expect from an algebraic context, but it is an inverse as an inverse function where the roles of the variables are switched. Y equals sine inverse of x. X is sine of y. Y is an angle. X is the value that's the sine of that angle. So y equals sine inverse of x means that what we're going to do is to assign to a number here the function value, the angle whose sine is x. Let's say that for an inverse function, algebraically, what happens is an inverse function and the function cancel out. So sine inverse of sine of u is u back, and in this case we'll have sine of u, so u is an angle, and an angle where we're considering this restricted domain between -π/2 and π/2, or the other way around, sine of sine inverse of v is v, where the number v that comes out is an acceptable value for sine of an angle. It has to be a number between -1 and 1. So from facts about the sine function, let's see what we can say about sine inverse. In general, you interchange the variables, and that has the effect when you're going from a function to its inverse of interchanging the domain and the range. So the domain of y equals sine inverse of x matches up with the range of y equals sine of x. That is, sine of x goes between -1 and 1, so that's where we're looking for values from sine inverse. And the range of sine inverse matches the domain of y equals sine of x. Those values come out as angles between minus pi over 2 and pi over 2. That's the restricted domain of sine of x that we're using to generate unique values for the sine function to make an inverse work. Here it is graphically. The red graph is y equals sine of x. So it goes from a low value, a low angle, minus pi over 2, and the sine value there is -1, to a high value of angle pi over 2, and the sine of pi over 2 is 1. These values correspond to angles in the quadrant 4, and these values correspond to angles in quadrant 1. So the inverse function comes from interchanging the variables y and x. That makes the graph reflected about the diagonal line y equals x, and we reflect the red line and we get the graph that's this blue graph. That's the graph of sine inverse of x. So sine inverse goes from a low value of -1 for x, and when we look at -1, the value y is sine inverse of -1. That means the angle whose sine is -1. The angle whose sine is -1 from that restricted domain is minus pi over 2, all the way up to 1 pi over 2. The angle whose sine is 1 is pi over 2. So let's calculate some values for angles that you might recognize from the special cases we've developed so far. Sine inverse of √3 over 2. So what we want is for y equals sine inverse of √3 over 2. That means y is the angle whose sine is √3 over 2. So sine of the angle is √3 over 2 with the restricted domain. Well, sine is positive in quadrant 1, and for the negative values it would be quadrant 4. But in quadrant 1, that would be where we'd look for a value. So we'd sketch in a reference angle in quadrant 1. And to make √3 over 2 come out from a 30, 60, 90 triangle, we should use angle pi over 3. 60 degrees makes the sine of 60 degrees √3 over 2. So that would be the choice. Another example, how about inverse sine of minus √2 over 2? Well, I recognize that √2 over 2 as being relevant to an isosceles right triangle. What I need to do is to interpret it in terms of where the angle is, and for the inverse sine, the angle is between minus pi over 2 and pi over 2. That puts the angle in quadrant 4 below the x-axis, or quadrant 1 above the x-axis. For the negative value of sine, we want to pick the reference angle so that we get a value of sine that's negative, that's below the x-axis. So we want to pick an angle theta that's negative between minus pi over 2 and 0. So sine is negative, and we can figure out where that is. √2 over 2 is the value that works with a reference angle of 45 degrees. That's pi over 4. So to make it negative, we'll pick in quadrant 4 the angle minus pi over 4, and theta is minus pi over 4. Now let's think about how it looks for another trig function. Instead of sine, let's do cosine. The same problem arises. For cosine, we have to worry about the fact that cosine is in general a multi-valued function. There are lots of angles that have the same cosine. That horizontal line crosses the graph of cosine of x lots of places. Every place it crosses for a particular horizontal line represents an angle whose cosine has that value. That's fine for a function, but it's not a one-to-one function. It's not a function that has an inverse. So the trick is the same trick. What we're going to do is take a set of angle values so that every value of the cosine function occurs once. Between 0 for the angle and pi for the angle, we watch the cosine values drop from the high value of 1 down to the low value of minus 1. So that every angle between 0 and pi is you can use to come up with a unique value for the cosine function. The cosine function would be 1-to-1 if you restrict the domain to be angles between 0 and pi. And that's what we'll do to come up with an inverse function. So I'm going to stretch out this interval from 0 to pi. I'll do that on the next slide so that you can see it to calculate a value of the cosine function. I've gotten lost here. Let me find where I want to be. Cosine. There's the I'm sorry, it took me a minute there. There's the inverse cosine function. There's a cosine function. What we'll do is use that to come up with an inverse function. So before there's the cosine function, and I'm looking at it from the interval from 0 to pi, and there is an interval where the cosine function takes on a unique value. So the inverse cosine of x is going to be on that restricted domain where the angle is between 0 and pi, and the x value is values of what the cosine function could be. Every possible value between minus 1 and 1 works. Here's what it looks like in terms of an inverse function. The idea is that the inverse function applied to a function value gets you back to where you started. So you start with an angle. Cosine of the angle is some number. Cosine inverse of the cosine of that angle is the angle whose cosine is what you started with, and that's the angle you started with as long as the angle is between 0 and pi. And the other way around, cosine of cosine inverse is back to the value of the cosine function, and that has to be a number between minus 1 and 1 as a y-coordinate of a point on, or an x-coordinate rather, of a point on the unit circle. So, thinking about how it works for algebraically defining an inverse function, for cosine inverse, the domain of cosine inverse is the range of the function it was a cosine of, that is values between minus 1 and 1, and the range is the domain of cosine of x, that is the domain of the restricted function, and we picked angles between 0 and pi, angles in quadrant 1 or 2, to make values come out. So the domain is numbers between -1 and 1. What you think about for the inverse cosine is plugging in possible numbers that could be values of the cosine function, and what comes out, the range of the inverse function, are the angles that would work. And angles in that restricted set are angles between 0 and pi. So here's a picture. We're going to do the same geometric approach of taking the appropriate restricted domain for the cosine function and reflecting that around the diagonal line y equals x to interchange the variables x and y to see this blue curve, which is the graph of the inverse cosine. Let's do a number. √3/2, if you're given that to calculate the inverse cosine, think about what would be so for √3/2 as the inverse cosine. We want the angle whose cosine is √3/2. You probably recognize that from one of the reference triangles that we've drawn. √3/2 shows up as a ratio of sides in a 30, 60, 90 triangle, and in that triangle we could use theta equals pi/6 to be the value that works. Another example, how about another triangle, this time cosine inverse of √2/2 with a minus in front? Well, √2/2 ought to ring a bell as an appropriate value of cosine for an isosceles right triangle with the minus out front. We just have to make sure we put the reference angle in the appropriate quadrant. So theta is cosine inverse minus √2/2. So cosine theta is minus √2/2. And with theta between 0 and pi, that puts it in quadrants 1 or 2. Quadrant 1 has cosine positive. Quadrant 2 has cosine negative. So we want the angle in quadrant 2. So an angle in quadrant 2 with cosine minus √2/2. An angle in quadrant 2 with an isosceles right triangle angle as a reference angle would be 3pi/4. Pi and pi/4, 45 degrees back from there. So we can keep track of inverse cosine in terms of what an appropriate angle would be. Keep track of it this way, that for the inverse cosine, the right place to look for an angle is in quadrants 1 and 2. That is an angle between 0 and pi. And when we're doing inverse sine, the right place to look was an angle between minus pi/2 and pi/2. That's an angle in quadrants 4 or 1. Now let's see what it looks like for tangent. The tangent function is, again, not 1-to-1. Tangent is periodic with period pi, and every time you step another pi units over, here to here to here, you get an angle whose tangent is the same. So a horizontal line intersects every branch once, and if you want to make a function that's 1-to-1, the approach is to restrict the domain of the tangent function. Best way might be to pick one of these branches and just use it. And a nice one to use is a branch that is symmetric about the origin. So let's pick this central branch, expand it a little bit, and look at what's happening between minus pi/2 and pi/2. That's one width of pi along the x-axis. That's one set of angle values on which the tangent function takes on each of its values exactly once. That's a good place to look to build an inverse function. So let's do that. The inverse tangent is going to be based on angles from minus pi over 2 to pi over 2, and the value that comes out for the inverse tangent function is the angle whose tangent is one of those reported values. So anything from minus infinity to infinity comes out as a value of the tangent function, and between minus pi over 2 and pi over 2 there is exactly one angle that goes with that. So y equals tangent inverse of x is the same thing as interchanging the variables. X is tangent of y. X is the angle whose tangent is y. So a numerical value for tangent goes with a particular angle value between minus pi over 2 and pi over 2, and what we'll end up with is the tangent of the angle as a number anywhere between minus infinity and infinity as a value of the tangent function. We'll plug in the y as the angle that yields that tangent as its value. Well, let's see where I am. I seem to have gotten lost in my slides again. This is a long set of slides. Okay, so there's my tangent graph. What's true about the inverse tangent is that we're looking at values of the angle between minus pi over 2 and pi over 2 that have a particular numerical value associated with that angle for the tangent function. And what makes it work is this general relation between a function and its inverse. Tangent inverse of tangent of u is u back, and tangent of tangent inverse of v is v back. The u that we're talking about here is tangent of u. We'd be taking tangent of an angle. So the angle is some reported radian measure between minus pi over 2 and pi over 2. And the v here is a value of the tangent function. The tangent function takes on numerical values between minus infinity and infinity for angles between minus pi over 2 and pi over 2. So, general fact about the relation between a function and its inverse. The domain of a function matches the range of the inverse function. So we're going to be looking for values for tangent inverse of x. We'll be plugging in values of possible tangent function values. That's any number from minus infinity to infinity. And what comes out when you apply that, the range of that function, is a set of angles that we will consider as appropriate values for the tangent function. And we can find an angle between minus pi over 2 and pi over 2 that works for any of those reference values. So the range is the set of values between minus pi over 2 and pi over 2. Notice that these are strict inequalities. Tangent of pi over 2, tangent of minus pi over 2 are undefined. And so we'll leave those out of the graph. Here's what we'll look at for the graph of the tangent function and the reflected function around the diagonal to interchange the variables. And watch what happens when you keep track of the restrictions on the domain and the range of the function and its inverse. The tangent function for the restricted domain goes from minus pi over 2 to pi over 2. And so the range of the inverse tangent function is that same interval from minus pi over 2 to pi over 2. Let's do a particular example. Minus root 3. Well, root 3 rings a bell for the tangent function. Remember, tangent is opposite over adjacent, and we could keep track of that for that particular value, root 3, in a labeled triangle that has the 30, 60, 90 triangle. So 1, 2, square root of 3. For minus root 3, we want to pick an angle that would be an appropriate reference angle for it to make a negative value of the tangent come out. And since we're looking at angles between minus pi over 2 and pi over 2, we're looking at angles in quadrants 4 or 1. And it's quadrant 4 where that happens. So we'll pick an angle in quadrant 4. Minus pi over 3 will give the reference triangle a 30, 60, 90 triangle to make the ratio of side opposite to side adjacent for the tangent function root 3 over 1, and we'll make it negative to go down to make it quadrant 4 for the appropriate sign of the answer. Here's another example. This time we'll tangle up the trig function's cosecant of cosine inverse of 1/4. Cosine inverse of 1/4. So we want to keep track of an angle whose cosine is 1/4. I don't know numerically what that angle might be, but I can figure out what it ought to look like. Cosine inverse of 1/4 ought to have adjacent over hypotenuse 1 to 4. So let's draw in a triangle that does that. Adjacent 1, hypotenuse 4. Put it in quadrant 1 to make that ratio positive, and that would be what it would look like. Now, for this reference triangle, hypotenuse 4, side adjacent 1, we could figure out what the side opposite the angle is by the Pythagorean theorem. Sum of the squares of the sides matches the square of the hypotenuse. Well, the only thing we don't know is this side, so we could figure out what it is by figuring out what the solution to the equation is. Y equals the square root of 15 makes y squared plus 1 squared equals 4 squared. So with the labeled sides 4, 1, root 15, cosecant is the reciprocal of the sine. Sine is opposite over hypotenuse for y over 4, y over r. Cosecant would be the reciprocal of that, r over y. So I'll plug in 4 for r, and the calculated value of y, square root of 15, 4 root 15 over 15, and that would be the value that comes out for the cosecant of the angle whose cosine is 1/4. We sketched the angle whose cosine is 1/4, and by labeling the extra side of the triangle, we could say what the cosecant of that would be. One more example. Let's do a numerical example, and this is really a kind of a cheat because there is an underlying triangle that you recognize. How about secant inverse of 2? We haven't talked about the inverse functions for secant or cosecant or cotangent, but we could figure out what's going on by applying a reciprocal identity. Theta is secant inverse of 2, means that we want an angle whose secant is 2. Well, an angle whose secant is 2 is an angle whose reciprocal has cosine equal to. 1 over cosine equal 2 says cosine theta equals 1/2. Now I'm back on familiar territory. Cosine theta is 1/2. I recognize as a 30, 60, 90 triangle. Theta is cosine inverse of 1/2. Now let me go back and show you cosine inverse of 1/2. If you didn't recognize that as a triangle you should know, you could get it from the Windows calculator. So let me start that up. There's the Windows calculator. I'd like cosine inverse of 1/2. So 1 divided by 2, if you didn't know that was 0.5, you could get it from here, 0.5. And what I want is the angle whose cosine is 0.5. Usually when you see an inverse trig function, you'll see it written in terms of radians. Let's answer it in radians. I want inverse cosine. So here inverse cosine of 1/2, and here's the value that comes out, 1.04 something. Now I don't know if you recognize that. You maybe could to see that cosine inverse of 1/2 means the angle whose cosine is 1/2. Well, pi over 3 is an angle whose cosine is 1/2 in radian measure, and this is pi over 3. Let me show you that it is 1.047 something, pi divided by 3, 1.047 something. It's a good bet. And we've got a value that works for the inverse cosine, and that's the right thing to consider to answer the original question for the inverse secant. Okay.